we're going to introduce the idea of functions. Learning objectives are: understand the idea of quantity, determine whether a relation between two quantities represents a function, determine whether a function is one-to-one, determine domain and range of a function, understand the process of composite functions, and find and verify inverse functions. So first, let's look at the idea of quantity. A quantity is any attribute of an object or process that can be quantified or measured. When we identify a quantity, there are always three questions that must be considered. So not always answered, but considered. So first is precisely what is the quantity? What unit of measure will be used to quantify it? What is the reference point for the measurement? So quantity may be constant or fixed, so it does not change. Or quantity may be varying, that means it changes over time or is not fixed. We typically assign a variable to represent changing measures of values of varying quantity, such as x, t, theta, or any symbol or letters to represent that quantity is varying. It is important for us to understand the idea of quantity because a function represents the relationship between two quantities, input quantities and output quantities. So next page, let's look at an example of a quantity, then we'll define a function. So let's look at this video. Suppose you place an empty glass to pour water so the glass begins to fill like this. So I'm going to play one more time. Then we can ask ourselves, what are some constant quantities in this glass filling process? So what are some fixed quantity? Such as volume of glass and height of the glass is fixed. It doesn't change. The glass height and the volume stays same. What are some varying quantities in this glass filling process? What quantities are changing? So such as height of water in the glass is changing as we pour the water, and volume of the water is also changing in the glass. So it is important for us to identify two different types of quantity so we can think about this relationship when we define a function. So a function consists of three parts: a set of input quantities, which is known as the domain of the function, and a set of output quantity, which is known as the range of a function, and a rule that assigns each input quantity to exactly one output quantity. So here, this is the important part. So all three are important, but each input quantity to exactly one output quantity. That means each input must be assigned to only one output. So essentially, a function is a relationship or rule that assigns an input quantity to exactly one output quantity. There are many ways to describe relationship or such a relationship using words, graphs, lists of order pairs, tables, and expressions. So next, we're going to look at example of functions given in table. And we're going to determine if each of given relationship between input quantities and output quantities is a function. So here we have set of inputs 0, 1, 2, 3. So 0, 1, 2, 3 is a domain of this function. And we can see 0 is assigned to -2. 1 is assigned to 3. 2 is assigned to 4. 3 is assigned to 4. So this is a function. Although 4 is repeated, that is okay. Only thing we need to worry about in terms of function relationship is that each input is assigned to one number. So this is a function because each input quantity is assigned to exactly one output. So let's look at second example right here. In this case, 0 is assigned to -2, That's good. But 1 is assigned to output quantity 3, and 1 is also assigned to output quantity 4. So this relationship, because of these, because 1 goes to 3 and 4, is not a function. So input quantity 1 is assigned to 3 and 4, so it is not a function. It still is a relationship, but that relationship is not defined as a function. So let's look at when function is given in graphs. Determine if each given relation between input quantities and output quantity is a function. So here, similarly, we have to look at the graph, and here let's see each input. So input value means x-axis in this case. Input quantity goes to only one output. So this is a function. Is a function. Here also similarly, each input value, for example, 4 is assigned to only one number, 1. 5 is assigned to, let me make it smaller, maybe about 0.5. 6, when input is 6, output is 0. When input is 9, output is negative 1.5. So each input has only one output. So this is also a function. This one, on the other hand, let's pick a point. So input quantity of 2 gives us two output. The one right here, about 2.1, and one right here, about negative 2.1. And again, this isn't the only input quantity that gives us more than one output, but 1 is enough to show that this is not a function. So circle, this is not a function. It still defines a relationship between two quantities, but it is not a function. This problem on your own. So pause the video, then submit your answer to the problem below in Canvas. You can find Module 1 video problems under Week 1 tab in our course Canvas page. So problem 1, does the below table represent a function? So this table. So this is yes or no question. Again, this is the format we'll be following just to encourage you and to keep you more engaged during when you're watching the video. And these are bonus problems. So getting problem wrong in these problem sets does not hurt your grade. It can only help your grade. So since this is the first time, I'm going to actually go to Canvas page and how you do this. So on the on our course Canvas page, in week 1 right here, you click M1 Module 1 video problems. So if you click this, and my view is a little different because instructor view, but you see a quiz view like this. So problem 1, select the correct answer for Module 1 video problem 1. And problem asking yes or no. Is this a function, yes or no? So you record your answer. Then maybe you can minimize your tab, your Canvas tab. Then keep watching the video, and video problem 2 will show up later in this video. So again, pause the video and submit your answer. And if you don't want to pause the video, you can also record your answer on your own paper and submit the problems, answers to problems after you watch the video. That works as well. So let's look at how we can write function using function notation. So function notation can be used to write function given an equation. So notation y equals f of x. So we write y equals f of x here because we use y-axis as output. So it defines a function named f. This read as y is a function of function of x, and x represents the input quantity. As I wrote here, the letter x represents the input quantity or independent variable. The letter y, or f of x, represents output quantity or dependent variable. So if you look at here, this is an example of a function f of x equals x cubed minus 2. So here, the one in parentheses, this represents the input variable, input quantity. So we're using x to represent a varying input quantity. And this f is just name. Sometimes we use f, g, h, v, any alphabet or any symbols we want to use to name the function. So we can call this function f. And this entire thing, f of x, that's how we read it, this represents an output. So this f of x right here represents an output. It symbolizes the output quantity. And this equation given right here is a rule or map that we follow to find a corresponding output for a input quantity. And this entire thing can be used to define a function, a specific function. So let's look at an example of using function notation. The height of winning pole vault in early years of the modern Olympic Games can be modeled as a function of time by this formula. So if you look at right here, ht, so function name h of t input quantity t equals 0.05 t plus 3.3. So we multiply 0.05 to t plus 3.3 to find the winning height. So here t is the number of years since 1900 and h is the winning height in meters. Calculate h of 4 and explain the practical terms of your answer, what your answer means. So here h4, remember this entire thing right here, this itself represents an output. It symbolizes what is the output quantity when the input quantity is 4. So in terms of context, it represents the height of the pole, winning pole vault, where you went t equals 4. So t is in years since 1900, so it represents the height of the pole in 1904. Then in order for us to calculate, we insert 4 as an input quantity. So in the equation, the t was here, so instead of t, we put 4 to calculate. Then we get 5.5 meters. So in practical terms, the winning pole height in 1904 was 5.3 meters. So a function can be used to calculate output quantity for a given input quantity. And it also can be used to communicate information, as you can see here. So let's look at more specific ideas around domain and range. From the definition of a function, the domain of the function is set of input quantities. So collection of all the input quantities. And range is function is set of all the output quantities. And we can express domain and range using set builder notation, interval notation, or some cases list all the quantities in domain and range. So what we're talking about right now is how we can express domain and range of function. So if you look at here, this is known as set builder notation. So this bracket means we have a set of numbers. So here's x is the input quantity. We use x as an input quantity that varies. And this bar right here, vertical bar, means such that. So we have x input quantity such that, and this is the range of numbers we have. We have x such that between greater than -2 and less than equal to 5. So input quantity domain of this function is all the numbers that is greater than -2 but less than equal to 5. So there are infinite number of quantities here. So this is set builder notation. The one on the right, this is known as interval notation. Here, what we have is -2 to 5. So this parenthesis here means not including -2. So excluding -2, we have number from -2 all the way to 5. This bracket means including 5. So these two way we wrote domain, these two represent same domain, same number of quantities in these two. Again, both have infinite number of them, but it represents same domain. And one last way we can express domain is listing all the values. So this is different from these, the one on the top. So here we list all the numbers. So in this case, we have 0, 1, 2.4, 5, and 6. So we have 5 numbers as domain. So here in this case, we have finite number of numbers, so we can list all of them. But in these two cases, we cannot list all of them because there are infinite number of numbers, infinite number of quantities between these two numbers. So that's why we cannot list it. Same here. So graphically, for a function on the left, so let's look at this example. Domain means all the input quantities. So input quantities are all the input, all the x values. So in this graph, we have input values from -5, and this closed circle, the fact that the circle is filled in, means we include the value -5. And it increases all the way. And this arrow means it goes forever this direction. So input, the domain, is x such that x is greater or equal to -5. Because it's closed circle, that means we include -5. That's how it would equal. So this is set builder notation. In interval notation, it will be -5 to infinity. And next to infinity, we always put parentheses because technically infinity is not a number. So we cannot actually include infinity. It's just showing the trend that number is bigger than -5 and anything bigger than -5, including -5. So then let's look at range of this function. So range is the output quantity, set of output quantities. So we look at y-axis. So if you look at here, the function goes only up to 5. So it will be -infinity all the way to 5. Same here, closed circle, that means we include 5. So in set-builder notation, we have y such that y is less than equal to 5. So all the numbers less than 5, including 5. And interval notation, -infinity to 5, and bracket means including 5. So we need to be able to express domain and range in both notation, set-builder notation and interval notation. So in this example, we have a function given in table. So we have input quantities are 0, 1, 2, 3. So here domain is just 0, 1, 2, 3. And range is all -2, 3, and 4. 4 is repeated. If it's repeated, we need to write only one time. So for this function, we can only express domain using listing all the quantities. That's the only way we can express domain and range here. We cannot use set builder notation nor the interval notation because we have finite number of input quantities and output quantities. So here's the general tips on finding domain and range of a function given in equation. So what do we do when function is given in equation? We don't have a graph nor table to find all the inputs and output. So exclude from domain any input values that result division by 0. And exclude from domain any input values that have non-real or undefined number outputs. And use valid input values to determine the range of output values. And the fourth step is like a verification. We can check our work by looking at the function graph if function is graphable, and table values to confirm the actual function behavior. So here, the reason why we say exclude from, that means that we begin with all real numbers. Then we find restriction from the given equation. So let's look at an example of finding domain when function is given in equation. So here, when we have a function in a fraction form, this is known as a rational function. So we have a function given in fraction. When we find the domain, we need to look at top and bottom function separately to find restriction. So you look at 2x, and are there any input quantities we cannot have? And as you can see, we can plug any values for x, and it will give us an output, just 2 times that input. So the numerator part does not give us any restriction. The denominator, on the other hand, we know that we cannot have a 0 on the denominator. So we have to use that fact to restrict the number to find the domain. So denominator cannot equal to 0. That means the denominator part of the function, which is x minus 4, cannot equal to 0. And we can solve for x by adding 4 both sides. So we know x cannot equal to 4. So this is the only number that we need to exclude from all real numbers for the domain of this function. Because if we plug 4 in, we'll get 0 on the denominator, so function will be undefined. So now that we get the idea of the domain, let's express this answer using set builder notation and interval notation. So domain in set builder notation is x such that x is not equal to 4. So it includes all the number but 4. So here, I meant to write interval notation. Domain in interval notation will be negative infinity to 4, union, so this means union. So we're including two intervals as a part of one domain of a function. Union 4 to infinity. So the parenthesis means excluding 4. So all the numbers up to 4 excluding 4, and all the numbers from 4 excluding 4 to infinity. So we're only taking away positive 4 from the all real numbers in this interval notation. So this is how we find domain of a function given an equation. So now we're going to look at a specific type of a function called one-to-one functions. A one-to-one function is a function in which each output value corresponds to exactly one input value. So one-to-one, the name one-to-one refers to one output for one input. So fx equals x is an example of a one-to-one function because each output is paired with one input. So let's demonstrate an example using table again. So here, in order to determine one-to-one function, first of all, it has to be a function first. So here we have a function in this left table. Each input goes to one output. But also each output, let's look at negative 2, is not repeated anywhere else. Negative 2 is only paired with input of 0. A is only paired with 1. D is only paired with 2. F is only paired with 3. So this function is a one-to-one function. Each output quantity is assigned to exactly one input. So it is a one-to-one function. And again, the simple way to think about it is output are not repeated by different input quantities. In this example right here, again, first of all, this is a function, but then as you can see, the output quantity 4 is paired with 2, 3, and 5. So this is not a function because output quantity 4 is paired with more than one input quantity. So it is not a one-to-one function. It is a function, just not one-to-one function. So how can we determine if function given in graphs are one-to-one function? So we can see here, pick an output. For example, output of, let me make it some 2. Output of 2 right here. Output of 2 has input 1 right here, maybe 2.1. And it also has input of maybe negative 0.5. And it also has an input of negative 1.8 about. So this graph is not a one-to-one function. It is a function, but it's not a one-to-one function. And another way to think about it is if we draw a horizontal line here, if it crosses more than 1, then it's not a one-to-one function. So this one is not a one-to-one function. This one is a one-to-one function because each input quantity is assigned to only one output, and output is also paired with only one input quantity. So this one is a one-to-one function. Again, you can also think of the horizontal line test. You can draw an imaginary horizontal line here and scan it up and down. And if it only intersects one at a one point with the graph and the horizontal line, then it is a one-to-one function. This one, the circle, first of all, this is not a function as we saw earlier. So it cannot be a one-to-one function. In order to be a one-to-one function, it has to be a function first. So it is not a function. So we can't even determine is one-to-one or not because it's not a function already. So this is the idea of one-to-one function. And there are many examples of one-to-one functions. As we saw here, mostly all the linear equations are one-to-one function except for the horizontal line. That's not one-to-one function because horizontal line shares infinite number of input values. So now let's look at composite function. So here I'm going to play a video. So this video will give you an overview of the process of composite function. So let me start right here. So here we have graph of two functions, g of x and f of x. And let's pick a value called a. So let's pick an input quantity a. And let's consider what it means to evaluate f of g of a. And we begin by evaluating a function g at input a, right here. We're going to evaluate this right here. Which yields, so let me actually show. So if I plug a there, this is the red arrow. G of a gives an output. And this value of g of a used as an input into the function f. So this blue segment, this quantity will be used as an input to function f. So let me go back to this symbol right here. We're evaluating g of a, which we got as the blue segment. Now this blue segment, which represents the output quantity, when input is a for g, we're going to plug in it right here. So g of a will be input, and it yields f of g of a. So this purple arrow, this quantity represents f of g of a. So if we think about the graph of a composite function, f of g of a, if we use as an input that the function f produce corresponding alpha value, and we'll put this together to plot the coordinate on one graph. So we just input a, and we're going to demonstrate right here, a comma f of g of a. So I inserted a as an input quantity, and we have f of g of a. So this point right here represents a comma f of g of a. So collection of all these points for all the input values will produce the function f of g of x, because x will represent varying quantity. So I'm going to play this video one more time for you to rewatch the whole process. What's happening when we composite two functions? So with a, we evaluate f of g of a to function g. Then we get g of a, and that g of a's output becomes input for function f of x. So whatever that quantity is, we input to the function f, and f of g of a is an output itself. So a comma f of g of a is a result of a composite function for an input, specific input a. And collection of all those points will make up the function, composite function. So this is just a one quantity, but collection of all these points will make. So next page actually shows what we just talked about. When we evaluate f of g of a, we input a, quantity a, into function g of x. Then we obtain g of a as an output. Then this output, g of a, is an input for function f of x. So on a new coordinate, we can plot the point a comma f of g of a. And collection of all these points construct a composite function. Composite function, f of g of x. So this is the process of composite function when we're thinking about in terms of graphs. So here we have two different graphs from the previous video. So it's different graphs, but process is the same. I input a, the inner function, in this case g. I put a into this function g right here. Then we obtain, so this height represents g of a. And I plug g of a into this quantity to function f, and this is f of g of x, f of g of a. So a composite function, composition of two functions, f of g of x is input to the function g, and the output, g of x, becomes the input for function f. So since we're plugging the input quantity to function g, the x must come from domain of g. So then the g of x becomes output for function f, and g of x will also be in domain of f, since g of x is behaving as an input quantity for f. When we plug in here, then we get f of g of x. And we sometimes write this circle f, open circle g. This symbol means composition. So let's look at an example composition of a function when functions are given an equation. So let's say I have a two functions. So I color differently so we can see how exactly this procedure works. So f of x equals 2 over square root of x plus 2. And g of x equals x squared minus x. And let's say I want to composite f of g of x. So f compose g. That's what this symbol means right here. This right here means composition 2. So the one that comes next, this goes to the inside of function f. So if this was g compose f, then we have g of f of x. So the one that comes first is the outside function. So this equals f of g of x. So this means right here, the function f of x is defined to be 2 over square root of x plus 2. Remember, x is the input quantity. X is input quantity. So right here, instead of x, for this entire thing, f of g of x, I'm going to insert g of x as an input. So on this equation, instead of x right here, I'm going to insert g of x. Like this, g of x. So the only difference between these two, because input of g of x instead of x, I put g of x. So then we're plugging in what g of x is in terms of its own equation. So instead of g of x, since g of x equals x squared minus x, I'm going to plug in x squared minus x right here. And this cannot be simplified furthermore. So this represents f of g of x, composite function. Before we move on, I'm going to have you try another problem. So pause the video, then submit your answer to the problem below in Canvas. You can find Module 1 video problems on the Week 1 tab in our course Canvas page. Okay, let me show you one more time, as I shown earlier in this video. Now you type your numerical answer to this problem. As you can see, you will not be able to see the actual problem in Canvas. You can only type the answer. So take as much time you need, pause the video, evaluate f of g of 2. So using these two functions given in table, type your numerical answer to f of g of 2. And when you're done, you can unpause the video and finish the rest of the video. So composition of function is very important because it will also help us define some other function in the next page. But it's important for us to understand the process, especially in thinking in terms of relationship between input quantities and output quantities. So here we're going to look at the idea of inverse function. So far we looked at just a function, definition of a function, one-to-one function, and composite functions. So we're going to get inverse function. So let's look at just a quick example. So this table represents a function. Each item is assigned to only one value, one output quantity, and output quantity here is grams of fat in each food item. So hamburger has 24 grams of fat, hot dog 19, fries 30, onion rings 25. So this table represents a function. So if I want to find inverse of this function, what we're doing is we're switching. If we look, so in this example, we look at items as an input. These are inputs, and these are output quantities. So an inverse function, we switch domain and range, which means we switch input quantities row and output quantities row. So this right here is an output function. As you can see, the grams of fat, we can now consider this as inputs, and these are outputs. But it is just more than switching the location of each table, location of the column. It is more than that. But this is just a very simple example to demonstrate. In inverse function, domain and range are switched. That's the main idea. But when domain and range are switching, there are a lot of things that are going on. So we're going to define that in the next page. So we have two definitions, and both are equally important when we're trying to understand the idea of inverse function. So first is that for a given function f, we form an inverse relation. Let's call it g, another function. So g and f are inverse to each other. By exchanging the coordinate pairs belonging to f. So for example, if a comma b, so a is input quantity, b is the output quantity. If a comma b is in function f, then b comma a is in function g. So we invert the process by switching or exchanging the coordinate pairs. So if g is also a function, then we say that f is invertible. So invertible means we can find the inverse function of a function, and that g is the inverse of f. If function f is invertible, then its inverse function is denoted by f inverse. So f to the negative 1 power, this is how we write it. And we read this expression as the inverse of f or f inverse. So here we express g, but if g is the inverse function of f, instead of writing symbol g or letter g, we can write g as f inverse to signify that g is actually inverse of f. That's why I put negative 1. And this negative 1 is not same as 1 over f. Okay, the same algebra rule doesn't apply here. That's not what's going on here. So this is what's happening when we're inverting. Just like we saw on previous page, we're inverting all the items, all the grams of fat. We switch domain and range. So these two functions are inverse to each other. So second definition is that we say that a function f is invertible. So invertible means it has an inverse function. If there is a function g for which if we composite f and g for all the domain of a, all the domain for f, so a is in domain of f. So if we do g of f of a, and if we simplify that equation, if we get a, and we also composite f of g of b, and we get b if we simplify for all b in the domain of g. So inverse function here, we're defining using composite function. So that's why the understanding of composite function is very important. So if I have a two function equation, in order to verify that those two functions are inverse to each other, all I need to do, let me go to the next page. All I need to do is composite two functions, g of f of a or g of f of x and f of g of x. And if I can simplify those equations to x in both cases, then those two functions are inverse to each other. Same idea. I want you to try this problem 3 on your own. So pause the video, true or false question. All functions are invertible. And you have an option, true or false, on Canvas, like this. So I won't be showing this Canvas page starting module 2 videos, but since it's the first time, so again, true or false, choose which one you think is correct, and submit the answer. Again, these questions are bonus questions, so getting it wrong will not hurt your grade. You only add it as a bonus to your grade. And because it's also bonus, these problems will not be extended in terms of due dates. So pause the video, try this problem, and unpause when you're done. So let's see the next page, what's happening graphically. So let me pause it real quick. So here I have a function f of x. So remember, the inverting a function is switching domain and range. So here, the x-axis represents domain. Y-axis represents range. So we're going to switch its role. So this domain will become range for inverse function, and this range will become domain for its inverse function. And the way we do that is by rotating over y equals x, this diagonal line right here. So if you can imagine y equals x line right here, diagonal line, we're going to rotate around that. So let me play the video. So we rotate like this. Let me pause it right here. So then, as you can see, the y-axis right here and x-axis right here. So now all these values are input for function f inverse, and this is the graph. And all the x value became output value for f inverse. So let me play one more time to show the inverting process. So you can also think as rotating around the y equals x line right here. Imagine an invisible line. So we just invert the function x cubed, and we got this as a graph, as inverse function. So let's look at here, using this graph, why we have y equals x, okay, as a symmetry. So you can think as the two graphs are symmetric around the y equals x, but more accurate way of thinking about it is we're rotating around y equals x, the diagonal line. So let's pick a number. So I'm going to try the composite 2 function. So if I do f of f inverse of 2, so let's look at this. F of f inverse of 2. So let's look at this first. Let's find the output. Let's evaluate this value. So f inverse is the green graph. So I'm going to plug in 2 into the green graph. And as an output, I get maybe about 1.3. Okay, so estimated 1.3. So instead of this inside f inverse of 2, I found 1.3 because that's what graph tells us. Then f of 1.3, so blue is the f graph. I'm going to plug 1.3 about here. Then we'll get 2 as an output. So what had happened here is f of f inverse of 2 gave us actually 2. Let's look at another one. Now let's do f inverse of f of 2. If they're inverse function to each other, then we should get 2. And let's actually verify these steps. So now I'm going to plugging in 2 to the function f. So I plug function 2 right here to blue graph f. And it gives me 4 right here. 4 as an output. Then I'm going to plug output quantity of 4 to the f inverse, which is green graph right here. Then if I plug 4 here, I get 2 as an output for green graph. So as we can see, the f inverse of f2 equals 2. So we can see that for this function, these two functions inverse each other. F inverse of x equals x, and f inverse f of x equals x. And when functions are given in equations, we can just do composite functions as we did earlier to verify that these two functions are inverse each other. But in order to show that two functions are inverse to each other, we have to verify this both of these. First, one with f inverse, and next with f inverse and f.